right. And we had Lyapunov's results, okay, on stability, saying that if we can find a positive definite function, okay, and if the derivative of this positive definite function is the time derivative, so the evolution of such a function is negative definite, then we have a stable equilibrium point. Moreover, if it's fully negative definite, so to speak, so not non-positive or not semi-negative, but just negative definite completely, then the origin is an asymptotically stable equilibrium point. Well, as we can see many times, this is not possible because it's not possible to assess from the very beginning. Mostly linear systems can achieve this condition, okay? So in general, linear systems satisfy two. Okay, they are a class of linear systems that satisfy the second condition. Most of the nonlinear systems, however, for most of the nonlinear systems, it's sometimes very difficult or maybe impossible to find such a Lyapunov function. Yeah, V is called a Lyapunov function. It's hard to find one having V dot negative. This is a difficult condition. Okay, it's a tough job to find this. And most of the times this is not possible. Whereas in the linear case, this is always possible. This is always possible, and we'll have examples about that. Okay. As I said before, this is only a sufficient condition. Hence, if you didn't find it, it doesn't mean it doesn't exist. It means you actually did not find it. You were not able to find that Lyapunov function satisfying the second condition. Okay, so it's not a problem of the system or a problem of the dynamics. It's a problem of how smart we can get. It's a problem of how smart we can get. Okay, and a very good example here is the pendulum. Whose Lyapunov function is its own total energy function. That is the kinetic energy plus the potential energy. Adding them up together, you can easily build a Lyapunov positive definite function, and then we assess the dynamics of the energy with respect to the time. Okay, clearly, in the origin, V of 0 equals 0, and V is positive definite on the domain between minus pi and pi because x1 is an angular position. Okay, so we can do this. Okay, and the derivative along the trajectory is okay, which is v dot x. We discussed last time, which is dv dx times x dot. Yeah, I just remind you, this is dv dx times x dot. Okay, is this one where we substitute here x1 dot and x2 dot. Okay, so this is actually dv dx times fx, where fx is the vector field describing the dynamics. Okay, and v dot is this guy. Now, how is this guy? This guy is not negative definite. It is not negative definite. It is semi-negative definite, or yeah, or not strictly negative definite. Okay, so even if k is non-zero, okay, this still can be zero for x2 equal to 0. Okay, so the origin is a stable equilibrium point, but we remember from the analysis of the last chapter of second order system that the origin is an asymptotically stable equilibrium point because the trajectories or the evolutions of the systems are attracted to the origin. Okay, they are attracted. The origin is an attractor point, so it should be or it definitely is, not that it should be. It definitely is an asymptotically stable point. Well, this analysis doesn't prove that. It doesn't prove that. But is this true? Is this true? Let's analyze now the behavior in the set, the behavior of the system in the set of the solutions of the equation Wx is 0. Let's analyze the solution of this equation. Okay, so this is always possible. This is always possible for any x between minus pi, x1 between minus pi and pi, and x2 0. What does x2 mean? x2 is the velocity, if you remember. Velocity equal to 0 means constant displacement. Means constant displacement. Hence, it follows that x2, this equation, so the solution here, Wx equal to 0 is always for x2 equal to 0, and x1 constant. So this is true for x2 equal to 0 and x1 constant. x2 equal to 0 means x2 dot equal to 0, implying sine x is 0. And the only point in this set in satisfying the above equality is the origin. The only point is the origin between minus pi and pi. Okay, between minus pi and pi, the only point is the origin. So the system is able to hold this equality only in the origin. So the variation of the energy, or the energy dies out only at this point. That means that V is strictly decreasing along any non-trivial trajectory x different from the 0. Okay, hence the origin is asymptotically stable. What does this mean? It means that the energy isn't like this. It's not like this. The energy is something like this. That's what this is proving. That's what this is proving. Okay, that's what this is proving. Okay. So how do you do this? This set Wx equals 0. That means that x2 equals 0 for all x1. This is the origin. But then the behavior is like this. x2 dot equal to 0. Okay. If x2 dot is equal to 0, then you get sine x1 equal to 0. Sine x1. x1 between minus pi and pi. That means x1 equal to 0. That's how we do this. That's how we do this. So the energy is constantly decreasing because W, you remember this. If you have a function fx, a scalar function fx, okay? This is if you get it like this, okay? This is f dot x equal to 0. Okay? This is what it is. F dot x equal to 0, you remember that. That's a critical point. That's a critical point. But you can have this for a whole interval. Well, this is not actually happening. So this is not constantly decreasing. This is not monotonically decreasing, yeah? Not monotonically. Not monotonically decreasing. Yeah. Whereas this one, this is monotonically decreasing. Monotonically decreasing. Okay. This is monotonically decreasing. That's what we prove here with this analysis. That's what we prove here with this very important analysis. Now, this analysis is actually part of what's called LaSalle principle. Lyapunov functions in the sense of LaSalle. LaSalle has extended this Lyapunov analysis, helping us helping us determine the asymptotic stability of an equilibrium point. Okay. So consider the system x dot is fx, where f is defined like this. F of 0 equal to 0. That means the origin is an equilibrium point. And consider D, capital D, to be a neighborhood of the origin. Assuming there exists a continuously differentiable function v, with v0 equal to 0 and v positive definite, such that v dot is non-positive definite, so this is like this, less than or equal to 0. If the set where wx is 0 contains only the trivial trajectory xt equal to 0, it doesn't contain non-trivial orbits. So if this set where the energy is not decreasing contains only the trivial trajectory, the equilibrium itself, then the origin is an asymptotically stable equilibrium point. Does this make sense to you? Physically, is this making sense to you? So if the origin of the system is the only trajectory where the energy is not decreasing, then that trajectory is drawing the energy towards it. Does this make sense to you? How am I going to explain this? Pendulum. Okay. Pendulum is swinging like this. Okay. So the energy, okay, it does like this. Okay, the energy is decreasing because the angle is decreasing. The energy is decreasing because the velocity is decreasing, yeah? Wx is minus k over m x squared, x2 squared, okay? So x2 decreases, that means wx decreases. So the energy, vx is decreasing. The energy is decreasing, okay? And then at a certain point, so the energy is decreasing. Is it monotonically? Is it monotonical? Monotonically decreasing. That's the question. Well, let's see where the variation of the energy. Let's see where is Vx equal constant. Vx equal constant means Wx, which is Vx dot, equals 0. Agreed? So let's see where Wx is 0. Wx is 0 means that the energy is constant for x2 equal to 0, so no speed, and x1 equals what? Well, x1 equals also 0. So the only trajectory where the energy is constant, is the origin itself. That means that if the only trajectory where the energy is constant is the equilibrium point and the energy is decreasing, it means the energy is monotonically decreasing. It means that the system is asymptotically stable. Does this make sense to you? Is this making sense to you?
Yes.
I suppose so. I don't know how to explain it better than this. Okay. Well, most of the times it's easier to apply this corollary is usually called the Lassalle's principle. Usually, most of the times, it's easier to use Lassalle's principle, so corollary 11, rather than the theorem of Lyapunov itself. Most of the times, it's easier to do this. Very nice principle. Energetic thinking, energy thinking from physics. This is very nice from mechanical physics. Okay. Now we can also determine the whole region of attraction. We can also determine the whole region of attraction because this Lassalle principle means that the origin is an attractor. We know that from the previous chapters. So the origin is an attractor. The origin is an attractor. So we can determine this region of attraction. We can do that. If the origin is an asymptotically stable equilibrium point, we can find the set of all initial conditions x0 from Rn such that initiating the trajectory, the evolution from any x0, from any such x0, finally, the evolution will go back to the origin, which is an equilibrium point. Okay, so we consider we consider the set of all trajectories where the energy is bounded by some constant. Okay, for all energies bounded. So because we start from a specific point. Okay, imagine you're holding your hand on this guy. So you start here with Vx smaller than some constant, because this is the constant. This is the constant because you holding the pendulum. Okay, holding the pendulum. Okay, and we can determine that is bounded and contained in D. Well, if this set is bounded and contained in D, then omega c is an estimate, of course, because you don't know a constant exactly, is an estimate of the region of attraction. Oh, you can go, no worries. And you can also interrupt me talking. You don't need to write to me. I know you're fascinated by what I'm saying, but you can communicate with me. Okay, go away. Okay, if you do that, I'll stop for a minute to go to the loo. Back in a second, please. I did not. gosh. Okay, fine. Okay, let's carry on. So I was saying, yeah, the origin where the energy is bounded. Okay, no, not the origin, the set where the energy we can find the region of attraction. Okay, we estimate it because we don't know. Okay, of course, for the pendulum it's easy. You can get any constant C here, here, anywhere, even here, if you like, because it will go back. Yeah, it's a very nice attractor, the origin for the pendulum. But this is not always the case. This is not always the case. Think about the mechanical oscillator. Okay, physics tells us the mechanical oscillator. Okay, you cannot stretch this because you can break the spring. Okay, you cannot take just any constant C. You just take C here. Okay, all right. Well, all we are discussing here, all the results we are presenting here, all of them, they're local results. They're local results. Okay, nothing is global except for linear systems. Linear systems are global. You know, have global results because the origin is the only isolated equilibrium point. Okay, and no matter where you go, no matter where you initiate or no matter where the initial condition exists for the linear system, if the linear system is stable, it will always go back to the origin. Okay, that's a special case, and that's due or thanks to the linearity, which is a wonderful property. Okay, so a few words about global stability, and one more thing. So all these results are very nice, and they can still be proven. However, for the case of global stability, very few complete results exist. You can look in the book of Khalil for global stability results. There are not so many. There is some very nice theory, but it's very difficult to apply. It is very, very difficult to apply. And people usually avoid that. Okay, so global stability is usually avoided. It's much easier to prove local stability. Okay, and sometimes global stability doesn't even exist. So the global stability means that the region of attraction is Rn, just like in the case of linear systems. So one has to find radially unbounded Lyapunov function candidates, which is this. That's why for linear system it's always true, because linear systems have this type of Lyapunov functions, quadratic functions. Okay. So if x transpose px, okay, so this is x1 xn p x1 xn. Okay, so essentially, and p, okay, you can write p in many ways. So this is a sum of xi squared pii plus sum of xi pij xj, quadratic terms. Okay, they're all quadratic terms. That means second degree, polynomials of second degree. Okay, so for this type of functions, most of the times you can prove. For linear systems, always you can prove, actually always, not most of the times, always for linear systems. And for nonlinear systems, sometimes you may prove global stability. I mean, that is, prove that the region of attraction is the whole Rn. An application of Lyapunov theory is the stability of linear systems. So now we really discuss linear systems as a special case, as a particular instance of the Lyapunov theory. The results that you know from linear systems about eigenvalues and that the eigenvalues should be in the open left half plane, actually these are consequences of the Lyapunov theory. Of course, when you study linear systems, it's difficult to do Lyapunov theory because you'd have to follow a nonlinear systems course before. You can't do that. You can't do that technically and from a teaching perspective. So when you study linear systems, they do use other arguments, valid arguments, expressing the idea of internal stability. However, it can be proven, and it's actually true, that the stability for linear systems is a particular case of Lyapunov stability. So we consider now the linear system x dot is ax. X dot is ax. Need I remind you that x dot is ax with the initial condition x0. Okay, initial condition x0. X0, so the following statements are equivalent. X0, x star equal to 0 is an asymptotically stable equilibrium point. If and only if the matrix A is stable, that is, the spectrum of the matrix A is in the open left half plane. Equivalently, there exists a symmetric positive definite matrix P, verifying the linear matrix inequality A transpose P plus PA is less than 0, is negative definite, okay? So positive definite matrices. I just recall M in R and a square matrix of order n is positive definite, and usually we talk about symmetric matrices when we talk about positive definiteness. Is positive definite if and only if x transposed mx, this is a scalar, this belongs to R, is positive for all x in Rn, for all x in Rn. This is the definition. This is the definition. Okay? And the characterization theorem, M is positive definite. This is how you write it, and we write okay. M is positive definite if and only if lambda I are positive for all lambda I in the spectrum of the matrix M. So all eigenvalues, all its eigenvalues are positive. All its eigenvalues are positive, okay? That's a positive definite matrix. Okay. That's why we say symmetric, because symmetric matrices have real spectra. Symmetric matrices have real spectra. Okay. Lambda M, this is the spectrum of the matrix M, is the set of eigenvalues of the matrix M. Did I remind you the discussion about eigenvalues? Have I recalled you? Have I made a recap of the discussion of eigenvalues? I can't recall. I think I did that in the previous chapter. The discussion. I did that for sure in the previous chapter. Okay. Right. Please do remember. Okay, the first two. So now we sketch the proof. The first two of statements. I would say statements, not assertions. The first two statements are clearly equivalent. We know that from linear systems theory. Why? We know that the solution is the solution of this equation using separation of variables is exponential of AT times x0. And check definition 8. What is definition 8? I can't remember what definition. Oh, this is definition 8. Okay. So we can prove that using this definition. You can prove that using this definition. Furthermore, for asymptotic stability, yeah, we know that e to the power at is t inverse e to the power lambda t times t, where lambda is we assume the matrix, for simplicity, we assume the matrix is diagonalizable, so the eigenvalues are simple and distinct. Lambda 1, lambda n. Okay, so that means that e to the power at, that means that e to the power at is e lambda 1t, e lambda n t. Now, question is, what happens to e to lambda it when t goes to infinity? When t goes to infinity, what happens? How can we assess that? So we assume that lambda I is sigma I plus minus j omega I. This is a complex number. Okay, with sigma I and omega I real numbers. Real numbers. Okay, so that means that e to the power lambda it is e to the power sigma I plus j omega plus minus j omega I t. So this is e to the power sigma. This is e to the power sigma I t times e to the power plus minus j omega I t. Right? Now, how's the limit to infinity? How's the limit to infinity? Okay. So we take limit when t goes to infinity in this guy. How much is that? How much is that? How much is that? This limit. How much is this limit? Tell me. Hmm? How much is it?
Depend
Yes, it depends on
the sigma.
Why not on omega?
I think because it will fade out.
Because
Because it's the actual the sigma gives the modulus, the amplitude.
both sigma and omega give the modulus. No, let me remind you. Limit when t goes to infinity from e to plus minus j omega it. How much is this limit? This is limit when t goes to infinity. How much is e to the power plus minus j omega I t? This is a complex number in the exponential form. How much is this? E to the power jx, how much is it? It's cosine x plus j sine x plus minus plus minus. So this is limit when t goes to infinity from cosine omega it plus minus j sine omega it. How much is this limit? The limit is in t. How much is it? How much is it?
It doesn't exist.
It doesn't exist. Very well. It doesn't exist, of course. It doesn't exist. But there is a but. But e to the power plus minus j omega it is what as a function? Is a what function? Is a how's the value of the function? It's always with respect to t. The value of the function with respect to t. It's always how? How's the function since it contains cosine and sine? How's the function? There is no limit, but the function is always it always can take it can always take values between -1 and 1, so it's always
It's bounded between that interval.
Bounded function, exactly. It's a bounded function. Very good. So this is always bounded, even if the limit doesn't exist. So what's the limit of this guy? Now we can assess. It's infinity, because you have, in the case, infinity times bounded, if sigma I is positive. Agree? And zero,
Yes.
0, because you have 0 times bounded. You're in the case 0 times bounded if sigma I is like this. And of course, you have no limit. It doesn't exist for sigma I equal to 0. It doesn't exist, okay, for sigma I equal to 0. So this is what happens. So it's very easy. So you can easily assess that this limit is 0 if and only if sigma I, so the real part of the eigenvalue, is negative. So the second and the first and the second statement, are equivalent, are strictly equivalent, just like the theory says. Okay. Now let's talk about the third statement, because the third statement is the interesting case. Okay, this is the interesting case. Number 3. So we have an if and only if statement. An if and only if statement, so we have to prove both necessity and sufficiency. First, we prove sufficiency. Yeah, so this is sufficiency. First, we prove the sufficiency. So we choose a quadratic form, Vx is x transpose Px, as a Lyapunov function. And we do Wx. I remind you that Wx is V dot x. V dot x. Okay? We need to assess the time, the evolution, the dynamic of the energy. So V dot x is what? How Leibniz rule of derivation. Okay? Leibniz rule. Okay? Leibniz rule. This is the Leibniz rule of derivation, okay? Leibniz rule. So is x dot transpose px plus xp, x transpose is here, x transpose is here, px dot, x transpose px dot. So now we just, okay, and what is x transpose? What is x dot? Sorry. What is x dot? X dot is ax. That means X dot transposed is X transposed A transposed. Okay, because transposition and time derivation, they commute. They can commute. Okay, so essentially you do this, and then you just get common factor in X transpose and X transpose to the left and X to the right. So you get this matrix. This is M. This is the matrix M. Okay. This is matrix M. So you get X transpose MX negative definite for all X non-negative. For all X non-negative. Okay. Look what it says here. Yeah, this is true. Okay. So it means that X star equal to 0 is an asymptotically stable equilibrium point. So sufficiency is very simple, is straightforward. It's straightforward. Okay. They say now let's prove that 2 implies 3. 2 implies 3. Assuming that we have a Q, we choose a Q positive definite, yeah, because essentially this is equivalent, or this is implied by saying there exists Q positive definite such that A transpose P plus PA equal minus Q. True? Actually, it's equivalent. It is equivalent. Okay? It's equivalent. So one can check that P equal P transpose defined by this matrix, is a solution of the algebraic equation of this Lyapunov algebraic equation. This is a Lyapunov algebraic equation. This is a Lyapunov algebraic equation. Okay, it's easy to check because if you put this, so usually you just write A transpose P plus PA equals A transpose integral from E A transpose T P, Q EAT dt plus integral from EA transpose T Q E to the power AT dt A. Okay, and when you do the integration, when you do this integration, okay, when you do this integration, you'll end up with Q. You'll end up with Q. Okay, here it's minus Q. It's minus Q. That's why it's negative, because Q is positive definite. Q it's positive. It is positive definite. Okay. All right. So you can very easily do the computations here. Yeah. You can do the computations here. Need I remind you that we have 2 implies 3. So in 2 we have this. So that means this is equivalent to that e to the power at goes to 0 when t goes to infinity. Okay. So we can do this. We can do this integration. We can do this integration. Okay. All right. Because you can integrate this and you can take it between 0 and infinity. Okay. You can take it between 0 and infinity. Essentially, this integral, this goes from 0 to infinity. This goes from 0 to infinity. So this guy is something like, because you have A transpose here. So this is, and here you have A. Okay. So this is something like E to the power A transposed T Q E to the power AT between 0 and infinity. between 0 and infinity. Why is that? Because if you look closely, yeah, actually, so this is integral from 0 to infinity from this function. Okay, let me put it this way. Okay, so what am I actually trying to show you here? Okay, so note that e to the power a transpose t q e to the power a t d to dt. First, Leibniz rule. You take this guy, so it's a transposed e to the power a transposed t q e to the power a t plus. Now you take Leibniz rule. You take the derivation of this guy. So it's e to the power a transpose t q e to the power a t times a. Okay. All right. You can do that. You can definitely do that. All right. So essentially, when you take the primitive of this guy, okay. So this guy, if you add it up, and actually, if you put a transpose here, and you put a in this guy, okay. So this is integral between 0 to infinity of a transpose ea transpose t q e to the power a t plus e to the power a transpose t q e a t times a dt. Okay, so it's essentially integral 0 to infinity of e to the power a transpose t q e a t prime dt. So this is e to the power a transpose t q e to the power a t between 0 and infinity. At infinity, they're all 0, and in 0, it's all minus q. So it's true. So this is very true. Okay, this is very true. So this is a solution. Okay, uniqueness is a bit complicated, but it's true 2 implying 3. Okay, now how can you check that P is positive definite? That's another question. How can you check P is positive definite? Okay, it's because of this integral and because it's Q is symmetric and positive definite actually. Okay, you can help yourself doing that. How can you do this numerically? You determine a P. You can determine a P solving an LMI 9. This is a linear matrix inequality, and there is in MATLAB there are many toolboxes showing you how to solve such an LMI. There is furthermore to assess the stability of a linear system using this Lyapunov way of thinking and the Lyapunov equation is a very numerically efficient algorithm rather than computing the eigenvalues of matrix A. So numerically, when MATLAB is checking the stability of a linear system, it's not using, and you can check that, it isn't using, it's not using eigenvalue computation and Schur form and all this complicated stuff, but it's checking this LMI thing. Okay. P can be chosen as a solution of the matrix algebraic, so P can be obtained from solving the Lyapunov equation number 10. Now the Lyapunov equation, it has efficient numerical algorithms to be solved. You can study that yourselves. I'm afraid that for very large dimensions of the matrix A, solving the Lyapunov equation is not so easy any longer. But anyway, okay, the second method is cheaper. It's also a reliable test deciding on the stability of the given matrix A. Okay. All right. Of course, you can prove the other results as well if you like. You can play with these proofs and check yourselves these things. So essentially, How can we assess the stability of a linear system? How can we assess the stability of a linear system? We take matrix A, we solve the LMI, we find the solution, and that's it. If the solution exists and is positive definite, then the linear system is asymptotically stable. Okay, now a corollary of this Lyapunov theory we have just seen is corollary 14. If you add to the LMI, if you add the observability property of the system, so if you can observe the system, then the system can be proved to be asymptotically stable. Okay. Essentially, if the pair CA is observable, I'm not sure if you remember what observability and controllability are from linear systems. Do you remember that?
Yes.
Okay.
The
Cool.
definition, how to find it out, but
sorry,
I don't know like how to like check for both, but I know what it means like in like a more general explanation.
So essentially it means that observability, okay, if so you have the system x dot is AX and Y is CX. If Y is 0, it implies X is 0. Okay, that's what observability means. Or even better, unobservability. If Y equals 0 implies X non-zero. Okay, so for this system, need I remind you that Y is CEAT X. Okay, where X is the solution of the first equation. Okay, actually X0 here. Okay, so if Y is 0 and implies X0 is not 0, then it's unobservable. The state X0 is unobservable. Now from this you get the observability can be assessed using a matrix criterion. You build a matrix Q, C, CA, CA to the power n minus 1. Okay, and the system or the pair CA is observable if and only if rank Q is n. This is observability. Essentially, in a nutshell, this is observability. So if the pair C is observable and the Lyapunov equation, this Lyapunov equation, and here you have C transpose C, this is the Gramian, the controllability, the observability Gramian, if you remember, has a solution X which is positive definite, then the origin is an asymptotically stable equilibrium point. So if the observability X is the observability Gramian, X is called observability Gramian, and it's actually integral from 0 to infinity e to the power a transposed t c transpose c e to the power at dt. Yeah, just like p, just like we had p earlier. This is actually q. Okay, this is q, but need I remind you that this is a semi-positive definite q. This is not positive definite. However, if the observability Gramian exists and is positive definite, then the origin is an asymptotically stable equilibrium point of the system. That's what it says. Okay. So what you do now, essentially, you take this Lyapunov candidate function and we assess stability. So we do v dot x, which is called wx. We do what we just showed in the previous case. So this is similar to P. Yeah, similar to what we did here. Okay, there is no big difference. Okay, so you get this. You get this. This is semi-negative definite. This is not negative definite, like in this case. So that's the difference between Q and X. Why? Because C transpose C is semi-negative definite. It's semi-positive, sorry, it's semi-positive definite. It's not positive definite. Okay, so you get this. You get this. This is a norm. This looks like a norm, like the Euclidean norm. This is the norm squared of the vector Cx. The norm of Cx squared. And with a minus in front of it, this is semi-negative definite. Hence, the origin is stable. Okay, it's stable, but is it actually asymptotically stable? Yes, we are going to use Lassalle's principle. We are going to use the principle of Lassalle, the one we just witnessed. We've just witnessed half an hour ago. Consider the set of points x for which wx is 0. So Cx equal to 0. Cx equal to 0. It means what? It means x transpose C transpose equal to 0. This is a linear equation in x transposed. So x belongs to the kernel of C. I hope you remember from matrix theory what the kernel is. So if you have a matrix M, okay, then kernel of M is the set of all x in Rn and times n. We can be also, it need not necessarily be square matrix, but even so. So the kernel of any matrix M is the set of all points x in our vectors in x in Rn with the property that mx equal to 0. X non-zero here. Keep in mind this. It's definitely non-zero. So this is the kernel of a matrix. So Wx is 0. That means that the set of the solution is the kernel of the matrix C. Okay? So the trajectories which are entirely contained in the kernel of C automatically belong to the so-called non-observable space, because it's Cx equal to 0. Of the pair CA. Cx is 0, Cx dot is 0, Cax dot is 0, and so on. But this is actually reduced to one single point because the system is observable. Yeah, you recognize here the matrix Q. Yeah, because you have from here, okay, if this is observable and this has rank n, this is equivalent to saying that Qx equals 0 if and only if x equals 0. Okay? Okay? That's what it says. Okay? Qx is equivalent with Cx, Cax, and so on. Ca to the power n minus 1 x equal to 0. Okay? This is due, so thanks to the observability, x star equal to 0 is the only point that makes that. So the kernel is only given by 0. That means, so this means kernel of C equal to 0. So if this is true, then by Lassalle's principle, so only the origin is the only trajectory where the energy is constant, where the variation of the energy is 0. The only place where the variation of the energy is 0 is only the origin. For the rest, the energy is decreasing. This is Lassalle's principle. Hence, the origin is asymptotically stable. hence the proof. Okay, so that's why any observable system with a positive definite Grahamian is asymptotically stable. Okay, you can have observable systems with Grahamians which are not positive definite, Okay? Then they're not necessarily stable. Does it make sense to you? Is it making sense to you?
Yes.
All right. I hope so. I honestly do.
Well, probably after reviewing the courses, it will be.
Yeah, but you have to recall some stuff from linear systems.
Yes, of course.
You and Andrei have taken the dimension reduction course last semester, haven't you? You took this course last semester, didn't you?
Yes, yes, indeed. Yes.
So that course, if you remember, I did a full half the semester was a recap of linear systems theory.
Yes.
So you should
Things
be
from
able
our
to
bachelor study.
observability stuff from the last semester. So this is the nonlinear way to look at the stability of things, of systems. Okay, this is the nonlinear way, and the linear systems are a particular case. They satisfy very nicely. They very nicely fit the Lyapunov theory. Okay, right. Okay, let's have a break and then we discuss another consequence or another result of the Lyapunov theory. That is the stability using the first approximation. Okay. Okay. See you in a few minutes. Okay, I'm back. I'm back.
I'm also here.
Oh, okay, lovely. Right. So stability in the first approximation. Okay, it's called Lyapunov's indirect method, whatever. So by first approximation, you remember we studied that when we had scalar systems, and then we repeated and discussed it because everything was based on first order approximation in the chapter for the second order systems, if you remember. Okay, so we kind of do this all the time, and first approximation is very important. Why is it called Lyapunov's method? Because it's going to be proven using the Lyapunov theory. So consider the system x dot is fx, continuously differentiable, okay, and we have a neighborhood of the origin. We have a neighborhood of the origin, okay, and we consider the matrix A. Consider the matrix A, which is the Jacobian of f evaluated in the origin. The Jacobian of f evaluated in the origin. Okay? And the result is like this. And we know this. We know this from second order systems. We know this from scalar system. If the spectrum of the matrix A is in the open left half plane, then all the eigenvalues of A have negative real parts. Okay? And in this case, the origin is an asymptotically stable equilibrium point. This is the main result, and this was to be expected. Okay, when we're happy about this. However, if there exists at least an eigenvalue which has having a real positive part, a positive real part, then the origin is unstable. Unfortunately, if you have at least one eigenvalue on the j omega axis, on the imaginary axis, then then we can't decide about this. Please note that this is all based, just like in the third chapter for second order systems. This is all a sufficient condition. It's not at all necessary. So it doesn't mean that if A has imaginary eigenvalues, you can have the system either stable or unstable. You remember the center behavior. Do you remember the center behavior? Yeah, the center behavior. A is 0 omega or minus omega, omega 0. If you remember this, okay, this was the center behavior. Okay, x2 versus x1 is like this, and it's undecidable. It's the structurally not stable, the structurally unstable behavior. So it can be stable or unstable. We can't decide. Remember that from chapter 3. Okay, so things you have to correlate chapter 3 with the results here in chapter 4. Okay, so we can't decide. So this is all sufficient. Okay, these are only sufficient conditions. They are not necessary. They are not necessary. They are not necessary, unfortunately, I'm afraid. Okay, how do we prove this? So using a mean value theorem, we can say that in the neighborhood of the origin, f can be written like this, can be expanded like this. It can be expanded like this, where so it's in the neighborhood of origin. So in the set between 0 and x, we can pick psi or zeta. This is actually zeta. We can pick zeta to to be something like this, and G can be considered to be this guy, because G, if you look closely, G is this guy. Okay. All right. G can be this guy. Okay. So we can pick that without loss of generality. We can, in the neighborhood of the origin, we can. These are all local results. Please keep in mind. I forgot to say. Okay. Local results. They are not global results. Okay, not at all. Global results. They are all local. So having this, okay, we consider we take any matrix Q positive, definite, positive, symmetric, and positive, definite. Hence, the Lyapunov equation A transpose P plus PA plus Q has a unique solution from the previous results, based on the previous results. Okay, and now we consider a Lyapunov candidate function. So the linear part is clear. Yeah, the linear part is clear from this guy. From this guy, you get this guy. Okay, all right. Now, you take this Lyapunov function and you evaluate v dot. V dot x is wx, and then you just substitute the derivative. X transpose x dot plus x dot p x. And now you just substitute fx. You just substitute fx here. You substitute it here. And substituting, you get two terms. You get the quadratic term, and you get the higher order term. This is quadratic. This is quadratic term. Yeah, this is a quadratic term. And because you have this equation, you can easily write this. Okay. Now consider gamma a positive constant. From the definition of G, we have that there exists another constant delta depending on the gamma positive, such that the norm of G can be bounded, upper bounded by the norm of x times gamma, for any x whose norm is upper bounded by delta depending on gamma. Okay, we can have that. Yeah. Hence, we may further deduce that the absolute value of x transpose pgx is less than, this is a scalar. Yeah, so this is a scalar. That's why you take the absolute value. This guy is a real quantity. Okay, so this is less than this, which is, remember that this satisfies this relation. So you take this relation and you substitute it here, and you can have that the absolute value of this function is upper bounded by this guy. Now you go back to the equality. Hence, wx is bounded strictly upper bounded by minus x transpose qx plus twice gamma norm p norm x squared, and this is what? Less than this quantity, and this quantity. Lambda mean is the minimal eigenvalue of Q, because the minimal one is the lowest value, gives the, yeah, this is minus, that's why we take the minus lambda mean, and this is twice lambda max this time. Lambda max times norm of x squared. And then we can choose a gamma at our discretion based on this majorization relationship, on this boundedness relationship. And then you can write this. This is true. Okay, this is true. And we use the following inequalities. Yeah. These are true inequalities which can be found in mathematics. Okay, and hence the proof that indeed the origin is an asymptotically stable equilibrium point if A is a stable matrix. If A is a stable matrix. So here in this proof, we just used the whole previous theory of Lyapunov functions and Lyapunov stability. Okay, so this is very nice. This is very nice. And here, in this case, this chapter ends with two examples. This example first. Sorry. This example first. Okay. This example where you have this V, and usually it's nice to check this is a Lyapunov candidate function. And in the second case is this guy, which you remember from the last time. And if you look at first order analysis of this guy, you get nothing. Let's just check this. Let's take it easy and check. So the first guy, the first example, number one. So V dot x, this is V dx times x dot, and dv dx, and vx, let's write vx. Vx is 5x1 squared plus 2x1 x2 plus 2x squared x2 squared, like this. Okay, so this means that dv dx is, this is the gradient, so it's a vector 10x1 plus 2x2, and then we have 2x1 plus 4x2. Okay, and hence then v dot x, which is wx, which is this guy, so it's 10x1 plus 2x2, and then 2x1 plus 4x2 times, and now f x2, and then minus x1 minus x2 minus 2x2 plus x1 times 1 minus x1 minus x2 squared. 1 minus x2 squared. Okay. Good. And now we just do the multiplication. This should be a scalar function. So this equals 10x1 x2 plus 2x2 squared plus 2x, sorry. Yeah, minus. So now we did what we did. We did this times this, and now we do this times this, plus, and we use the signs. So minus 2x1 squared minus 2x1 x2 minus 4x1 x2 plus x1 times 1 minus x2 squared. Okay, plus minus 4x1 x2 minus 4x2 squared minus 8x2 times x2 plus x1 times 1 minus x2 squared. So we have to assess this quantity. God forbid. So we need to assess this term. So this is here what? Minus 8x2 squared plus minus, no, so minus plus 8x2 x1 times 1 minus x2 squared. So this further is minus 8x2 squared minus 8x to x2 to the power 4 plus 8x2 x1 minus 8x2 to the power 3 x1. True? So we have to do it like this. And then we have to further do the computations. So let's take the time x1, x2. This one, this one, this one, this one. True? So this is 10, 8, 4, minus 4, x1, x2. Okay, then we have from this guy, this is unique. Yeah, so it's minus 8x2 to the power 4. This is also unique, minus 8x1, x2 to the power 3. Okay. And here you have minus, so then you have this guy and this guy and this guy. Sorry. And this guy. So minus 2 minus 8. This is minus 10 x2 squared. This is kind of everything. Okay. And this can be manipulated further to look like this is semi-negative definite. Okay. Semi-negative definite. And then you may use LaSalle. You can check it further. You can check it further. Okay. And you can also do the phase plot and see what happens. Okay. And also you can try the stability of the origin using first order approximation. The first order approximation in the origin. Okay. First order approximation in the origin. Okay. So you have this guy, this is fx, till example 1, df, dx. So you have multiple ways of checking stability. That's what I'm saying. You just have to try. So this is 0, 1. Then you have minus 1. Well, this here is what? 2x2 minus 2x2 to the power 3 plus x1 minus x1 x2 squared, and everything with a minus in front of it. So it's minus 1 minus 1 minus x2 squared, and then df2 to dx2 minus 1 minus 2 plus 6 x2 squared minus 2x2 x1. Okay, and then A is df dx in the origin. So it's actually 0, 1, 0, 1, minus 2, minus 3. And this is a companion matrix of the following characteristic polynomial: lambda squared plus 3 lambda plus 2. This is a Hurwitz polynomial. So indeed, this means that the origin is asymptotically stable. So here the first approximation works. So here you have to prove using LaSalle. Using LaSalle, you have to reach the same result using LaSalle's principle. For the second example, number 2, okay, the first order approximation fails, they say. Let's see. So df dx in 0 is, I'm just trying to do it quickly, minus 2 mu x1, no, minus 3 mu x1 squared minus mu x2 squared. Okay, hold on a second. What happened here? Hold on a second, please. I just got a document I need to look at. Oh, okay. Okay. Sorry about that. And the second one, so x2, it's 1 minus 2 mu x1 x2, and then you have minus 1 minus 2 mu x1 x2, and then you have a function. You have a function here. It's very easy to see that you have something probably similar to this one. Okay, and sorry, similar to this one. Okay, and if you take this in 0, 0, this equals 0, 1, 1, 0. This is undecidable because this has the eigenvalue. This has the eigenvalue lambda of A plus minus j omega. Okay, so cannot decide. However, what it says here that if you go to polar coordinates, so x is r cos theta x1 and x2 is r sine theta, you'll get, okay, so in polar coordinates, however, in polar coordinates, okay, in polar coordinates, you get R dot, if I remember correctly, it's something like R times R minus 1, something like that. Okay, and theta dot is 1, something like this, if you remember correctly. Okay, and in this case, you can decide the neighborhood, you can decide what happens with the equilibrium point here. Okay, and what happens to the origin. Okay, so if you change the coordinates, you may find out something very interesting. And it's identical to what you find for the original system. Okay. All right. Well, there are some written note exercises. Let me check if I have them here. With more exercises, and then I'll try to show you also something in Maple. And you can also, and maybe also in MATLAB. And later on, you can work it out yourselves. Okay? And you can do the assignments. Please don't forget about the assignments. Okay? Do your assignments to get the points, please. NLC, exercises, notebook. You have some exercises here. Where is it? Well, an interesting example, actually, I would like to show you before anything else is this one. If you take the classic mechanical oscillator, the linear mechanical oscillator, okay? So linear example. Linear mechanical oscillator. Linear mechanical oscillator. That means we have an equation of the type y double dot, say, plus by dot plus ay equal 0. Okay, with AB positive, AB positive. Okay, assess the stability of the origin. Assess the stability of the origin using the Lyapunov stability theory. How do we do this? We have three options. Option number one. So first of all, we have to write this in first order. So x1 dot is x2. You remember that, and x2 dot is minus a x1 minus b x2. Okay. Right. Now, we'd like to find some Lyapunov functions. This is a linear system. So essentially, you can write this x dot is ax with the matrix A, 0, 1, minus A, minus B. Of course, you know from linear systems theory that this is the companion. So the characteristic polynomial of this guy, is lambda squared plus b lambda plus a, and since a and b are positive, this is Hurwitz, and you know that the origin is stable. How do you assess that through Lyapunov theory? What am I trying to show you here, actually? So you can find several Lyapunov functions. Okay, let's find a Lyapunov function. Let's find a Lyapunov function. The first Lyapunov function that comes to mind, so the first one is Vx equals x1 squared plus x2 squared. So position squared plus velocity squared. So potential energy plus kinetic energy, half. Then dv dx is x1, x2, and v dot x, which is wx, which is dv dx times fx. Okay, this is fx. Okay, this is fx. Okay, so it's x1, sorry, it's x1 x2 times x2 minus a x1 minus b x2. Okay, so this is what? X1 x2, this times this, plus this times this, minus a x1 x2 minus b x2 squared. So this is not right. I need something else. So I need here times a. So if I need here times a, I'm taking here a. True? Is this correct or not? No. Actually, I'm taking here times what? No, I said I was right. Times a. This is from the elastic stuff. True? You agree? So I'm taking it like this. So here I get a x1 x2 minus a x1 x2. So these cancel each other. So this is minus b x2 squared, which is semi-negative definite for all x2 non-zero. Actually, for all x2. Sorry, for all x2. And here, using LaSalle, so here, use LaSalle, okay? x2, wx equals 0, implies if and only if x2 is 0, which means x2 dot is 0, which means actually that x1, if you look closely here, this is the equation. X2 dot is 0, x2 is 0. You get ax1 is 0, which is 0 since a is non-zero. X1 is 0, the unique solution. So using LaSalle, the only constant energy you get for 0, that means that 0 is asymptotically stable. On the other hand, you may choose x trans v to be v. We choose v. Sorry. V to be Vx actually. Okay. Choose Vx to be half x transpose Px. X transpose Px. Okay. With P the solution of the Lyapunov equation, A transpose P plus PA equal some minus Q. Let's take it minus identity. Because it's the easiest way. Okay. Keep in mind that P is symmetric and positive definite. So P may be chosen A1, A2, A2, A3. Okay? And we can solve this guy. A transpose is what? 0, 1 minus A minus B. So you have 0 minus A, 1 minus B times P, which is A1 A2, A2, A3 plus PA, A1, A2, A2, A3 times 0, 1 minus A minus B equal minus 1 minus 1. And solve this system of two equations into unknowns. Okay? Okay? We can solve this. Oh, sorry, forget about the notation is bad. I should have used P. Anyway. So it's, we get minus A times A2. Minus A times A3 plus minus A2 and what else? Plus, am I doing this right? No, I'm not doing this right. This is wrong. Okay? So I'm doing it wrong. Okay? So this is minus A. Minus A, A2. Plus minus A, A2 equal minus 1. This is the first equation. Then the second equation, minus A, A3 plus A1 minus A2B plus A1 minus A2B equals 0. And the third equation, because it's symmetric, you have only one more, this corner. Okay, so it's minus AA3 minus A3B minus B A3 is minus 1. And here you get A1, A2, and A3. A1, A2, and A3. Okay, for instance, A3 is what? 1 over B minus A. Okay, and here you get that A2 is 1 over 2A, something like this. I hope I'm right. I'm not sure if I'm getting this right. And then here you'll get A1 to be something. Well, so it's more complicated to write this V. This is more complicated than Vx equals half x transposed x, the previous one. Much more difficult. But V dot x in this case is like this. Whereas in the previous case, you are supposed to use the LaSalle principle. So you see? So what I'm trying to tell you here is that the Lyapunov analysis is not unique. There isn't only one. That's why the result is if there exists A, because there might exist even more. No one says if there exists a unique A, a unique V. So V is not a unique, yeah? The Lyapunov functions are not unique. That's why I'm saying this is sufficient. If you didn't find the Lyapunov function, it actually doesn't mean that it does not exist. Okay. All right. Have you got any questions for these lectures? Any questions about this lecture? Hmm? Yes,
I'm
please.
again in my language course, so I won't answer if you're asking questions because I can't focus on both things at the same time.
No, I was asking you if you have any questions about the lecture.
So far, not. So we have to look. Maybe I will see the record, the record, and then I will the recording, and then we will come back to you if I have any questions.
Yes, please do that. I'm trying to show you something in MATLAB now, in Maple, some examples. So, yeah, and see how everything works. Okay, just bear with me a minute. I'm waiting for the MATLAB to open, to start. Okay, share screen. Lyapunov stability testing. I want to show you. Okay. Look. I'm setting up. Can you see the screen?
Yes, the MATLAB window.
Okay, the MATLAB window. Very nice. So you set a tolerance, and I'm here generating a random matrix of order n by n. And I'm taking here the Q matrix to be the identity matrix. Okay, and then I'm solving the Lyapunov equation This is the command for the Lyapunov equation. E transpose P plus PA is minus Q. Okay. And then these are the commands. These are the commands helping us identify or test, helping us to test, okay, the Lyapunov stability, okay? So this is essentially the Lyapunov stability, not the Lyapunov, sorry, the Lyapunov LMI stability testing, okay? This is the one, okay? And if you do this, so these are the commands, okay, and this is the result. So this is a huge matrix you see here. That's why I'm taking 10,000, because for small matrices you can compute the eigenvalues, but for large matrices this is not possible. This is not possible. Okay. Okay, let's start first with a small matrix, n order 10. Let's try this first. Okay. A is not really stable because, so this is a random matrix, okay? You see A. This is the matrix A. So it's not really stable. Here we can compute eigenvalue of A. Yes, indeed, it is not stable. You see, these eigenvalues have positive real parts, hence it's not stable. It is not stable. Okay, let's generate. Let's see if we can generate a stable matrix. Here we can take minus, I don't know, 10 to the power 3. Let's see if we can do that. But I'm not sure if this is working. And I'm trying to force a stable matrix. Is asymptotically stable this time. You see? The same test. The same test. A. Yes, indeed. Look, it's very, very stable. It's very, very stable. You see? Very, very stable. You see? But this test is very efficient because now we are going to increase the dimension. We're going to increase the dimension. Let's go to 100. Asymptotically stable. Okay, maybe this is too much here. Maybe I should take here 10 to the power 2. Let's try this again. It's asymptotically stable. Okay. Sorry. Egg. Okay. You see? Indeed, it looks like it's asymptotically stable because we can still compute the eigenvalues. We can still compute the eigenvalues. Okay. We can still compute the eigenvalues. Maybe 10 should be enough. Not really stable this time. Okay. So indeed, we should take here to the power 2. Is asymptotically stable, but we can still compute the eigenvalues. Let's go to 1000. Lyapunov testing. Well, it takes a while. Not really stable this time. Let's see. Now you see it's very difficult to compute the eigenvalues. Maybe there are some which are positive. Let's see. Have you seen a positive one? They're usually ordered. Yes, you see, it's an unstable one this time. It's an unstable one. Okay. Let's go now to 10,000. 10,000. Run. It's testing the LMI. Let me stop this. I made a mistake here. Hold on a second. Oh, crap. I think this guy is blocked. Sorry for that. Hold on a second. I'll try again. I'll try again. Try again. Just bear with me a second. Okay. Okay. Let's do this again. What happened? Florian has left.
He didn't anything.
Can you speak louder, please?
I don't know. He didn't write anything in the chat.
No, maybe he just dropped. I'm trying to get some result about the testing, but I'm afraid that my PC is a bit slow and it's not working. I was trying to show you for 10,000, for n equal to 10,000.
Anyway, I can no longer see your screen.
Yeah, I know, because I stopped the share screen. I'm just trying to see if it works. I know that. Anyway. Well, it doesn't seem to be doing anything. Let me try to share again. Can you see the screen again?
Yes.
Okay. Well, nothing pretty much happens because it's still busy testing. You know? Well, I'm just going to stop, but you get the idea, okay? Actually, I think you all got the idea about this, the testing of the Lyapunov stability using LMIs, okay? Using LMIs. It's much better than to keep computing eigenvalues, okay? This is the main idea of these things. Yeah. Okay. It should stop somehow now. I'm afraid it does not.
As far as I know, if you try to stop MATLAB while it's computing something, it will crash. You have to kill it.
That's what I'm doing. You see, I'm killing it, trying to kill it. Okay. Hope it's doing something. Okay. I think this is a bit too much for my PC. Anyway. Okay. So it stopped. Let's go now to Maple. I hope Maple works. Oh, MATLAB is not killed. What the hell? MATLAB is still showing here, you see? Very strange. I want to show you some examples of computing Lyapunov functions. You hear me?
Yes.
Okay, fine. And let's wait for Maple to start. Oh, Florian is back. Good. Just bear with me for a few minutes. We'll be on the right path soon. Don't worry about it. I advise you to read in the book of Khalil. There's many details in there. Okay, there's many details in there. Okay, Maple is starting. This is a good sign. It started. Even better sign. Oh, no, not save, but open. Because I'm not saving anything. Okay, so Lyapunov functions. Okay, we have some problems here. Lyapunov function for the pendulum. Let's have a look. Okay. So we've got this system. So this is not the pendulum. I'm not sure why this is called pendulum here. But we've got this polynomial system. If you look, x dot is y and y dot is minus x dot minus x square y. Okay, this is a polynomial. Okay, and this is the Jacobian. This is the Jacobian, and here we see we check the Bendixson condition for the limit cycles. Okay, here you can very clearly see we have the origin as an equilibrium point, and the matrix A is a matrix whose eigenvalues are on the j omega axis. So the first approximation doesn't tell us anything. It's not telling us anything. Okay, and here, for instance, I have a Lyapunov function. I have a classic Lyapunov function computed. Okay, and here I use the gradient. Here is the gradient of the Lyapunov function, and here is the W. So this is V dot. This is V dot. Okay, and here I'm solving when this V dot can be negative. This V dot can be negative. This is the solution of this guy. Okay, and here I'm checking the solution where it can be 0. And here, actually, if you use Lassalle's principle, you may come up with the origin to be an asymptotically stable point, essentially. Okay, so the first approximation doesn't tell you anything. If the first approximation isn't telling you anything, you can go search for a better Lyapunov candidate function. Okay, and I'm passing everything in polar coordinates, and in polar coordinates I can see, you see the W in polar coordinates, just like I told you in the last example of the lecture. Okay, in polar coordinates things are more clear. This is negative definite, semi-negative definite. Okay, for all r and theta, and it's actually no. This is actually a negative definite completely. Actually, this is negative definite, not semi-negative definite. This is negative definite. Okay, this is negative definite. And indeed, if you remember, R is an attractor. R is an attractor. Okay, in 0. R is an attractor in 0. Okay. And indeed, you remember the limit cycle thing. Okay? Very interesting. So limit cycle done with some Lyapunov reasoning. Okay. Then we have what? We have this. Okay. Let's make it like this. We have this system. This polynomial system. Here x dot is y dot is minus x minus y minus, so this is the example in the lecture, if you remember. This is the example in the lecture. And this is the Jacobian. And this is the, you see here we can have, so essentially there is the possibility to have a limit cycle. Yeah, because this can be 0. The origin is the only equilibrium point. And if you look here closely, the origin is actually asymptotically stable. Just like we discussed. And we have this Lyapunov candidate function. I don't know who cooked it up, but this is the W. This is the W here, if you look closely. This is the W. And it's a bit difficult to use the W to show something. However, if you look closely, if you go again to polar coordinates, maybe it's easier to say something about the Lyapunov function, which is this very simple function in polar coordinates. Okay. So sometimes things are not so easy. Okay, and this is the node behavior of the origin. Okay, this is the node behavior of the origin. Then we can check this guy. Another example. So another more complicated polynomial dynamical system. Origin is the only equilibrium point. We have a center behavior, so the first order approximation isn't telling us anything. So we use the Lyapunov, we use this simple quadratic Lyapunov function, and we can see that this is negative definite. This is negative. This can be actually negative definite, because if you take it 0, both of them have to be 0. So even by LaSalle, only in 0, this is 0. Only in 0, this is 0. In polar coordinates, it's even easier to check. Here you can use LaSalle principle because this is semi-negative definite. And here R is in 0 is an attractor, if you can check. And then, since R exists and is an attractor, you have a small limit cycle behavior around the origin. So going to polar coordinates tells you a lot of things when you have polynomial things, when you have polynomial systems. Okay, so you have very nice stable oscillations, just like you'd like to have. You'd like nonlinear systems to exhibit if you want oscillations. Other examples. This example, for instance. Yeah. You see? This example. But this is positive definite, so there should be a minus sign somewhere. Okay. And polar coordinates. Look here. Yeah. And here you can see that actually the origin is not stable. The origin is not stable over, well, no, it's not stable because the equilibrium point goes, this one goes to number 2, doesn't go to the origin. So the origin is not a stable point, but the other point is a stable point. Okay. And probably you have more equilibria, and the other equilibrium point is stable. And the last example is this one, which is very complicated because you have coefficients. Okay. We have coefficients and we have the Lyapunov. Look, an interesting Lyapunov function, which is more complicated than usual, containing this term. And W in this case is this guy, and you can use the LaSalle principle. So this is semi-negative definite, and then using LaSalle principle, I think you can show that the origin is an asymptotically stable equilibrium point. So essentially, I invite you, this is a third order example if you look here. So this is an nth order, so this is a third order example. So I actually invite you to study all of this and to do your assignments, please, okay? And next time, I'll try to show you some written examples of Lyapunov stability, some notes I have. Next time is in 2 weeks' time, okay? So next time is on the because there's short holidays then, and the next time we meet each other is on the 8th of December, okay? We meet on the 8th of December, all right? Okay, if you have questions, remarks, please. Questions or remarks, please. I'm listening. I'm listening, please. If you have anything to tell me, if you need some, is there anything else I can help you with?
Maybe I have one question.
Please.
Regarding if there is some book you can tell me about, which would be really good to get a basic understanding of linear systems, because I'm
Linear or non-linear?
okay.
Linear or non-linear?
Linear, because I have the problem that I'm not that familiar with the linear
Oh, you're
systems.
familiar with linear systems. Okay. So I'm going to hold on. Let me go. Okay, fine. I see your problem. I understand. Let me try to help you somehow. Okay, so I'm going to the files. Okay. I go to the file section, right? And I'm going to put here class materials. Oh, there's nothing here. Why? Ah, Maple, you have recordings, Maple. Okay, class materials. Okay. And here I'm going to upload a book, the book of Antulas, where there is a short study about, I think there is a short study about linear systems. I've got many books on the subject. And I'm also going to give you some, I'm going to show some lectures if you're interested.
Seconds. I don't know if I'm, yeah.
I have some lectures, my lectures on linear systems.
It would be nice, because the problem is I'm currently trying to get a better understanding of the background.
Yeah, I understand. I see what you mean. I'm
Yeah.
going to give you from this. These are lectures that, for instance, teach in the course that doesn't exist any longer of the course that doesn't exist any longer of dimension and complexity reduction, because well, the master I don't think is going to be next year. Okay, so you can read this. This is in English, so they are nice lectures in English. So 2, 3, 4. Here you get 3 lectures about linear systems. First of all, okay, and furthermore, I'm going to give you a book. I'm going to give you a book on linear systems. There's many books everywhere. You can have books of linear systems. Let me see which one is nicer. Isidori, no. Khalil, you know. Kailat, no. Kailat is not good for you. Oh, crap. Which one is better? This one is in Italian. No, let me try this book and see if you can get something out of it. This book. The introduction, the first few chapters of this book, not all of them. Just look in the table of contents and select what's useful for you. Okay, so if can you go to the files section in Teams, please? Dorian, please go to the files section.
Yeah, I'm on my way. I was on the files section in on Moodle or.
No. I'm talking about Teams class now.
Yeah, I'm on my way.
Yes, please.